Good morning, dear all. Today we start study the elements of vector theory, and we began to work with solid and multidimensional geometry. On the three first lectures, we consider the plane geometry, and we based on the axiomatic methods due Euclid. Today we start with so evident notion of physical space. We will consider physical space as a set of points. Point is a small object, and various points the same, and all arithmetical magnitudes, all algebraic magnitudes. We used numbers and some equations, inequalities for such description. This approach based on the notion vector. What mean the vector? We can imagine two such points in the space and some segments, but we suggest that one of these points is initial point and other endpoint, and we suggest that this segment has orientation or direction from initial point to the end point, and such arbitrary segments with direction we will denote using its endpoints as AB with arrow, and also we will use small Latin letters for as notion for such objects. We also consider two such objects. For example, one vector AB and other vector CD, and if such vectors are parallel, have the same length and the same orientation, such object will call equivalent. More precisely, definition 1. Two vectors are equivalent if they are parallel the same length and the same orientation. Parallel and the same orientation is the same direction. We also will say that such vectors are equal. Equal, not strict sense. In our language is equivalent, more strict notion. We can imagine that in arbitrary points of the space exist such vector which equivalent the initial vector AB, and we can imagine this set of all vectors define some motion in the space, transition, and we can identify some this all equivalent, the set of all equivalent vectors with some motion, with transition. And this observation help to us understand better the notion of vector. The other definition, the vector is transition in the space. We will denote by letter S the space. S is the space, and by V up 3 we will denote the set of all vectors, all vectors in the space. Let's fix some point O in the space, and we will consider the set of all vectors in the form OA, where A is the point of our space S. This basic set in our consideration. The set of all vectors. Arbitrary vector in the space is equivalent to the vector of such form. We have some bijection between space S and the space of such vectors V up 3. And this bijection is defined by the following correspondence. V corresponds to point A, the vector OA. And easy to see that this correspondence is bijection. The various vectors are corresponds to various point, and for arbitrary vector exist unique points which corresponds to this vector. We also consider the some vectors which has coincide initial and end points, OA or equivalent vector AA. Such vector we will call zero vectors and denotes by letters O. More interesting things that we can define on the vectors some operation. First of this algebraic operation is the operation of sum. This operation corresponds to the superposition of the transition, if vector understand as transition in the space, on such maps naturally defined the operation of composition, and this operation corresponds to the operation of the operation sum on the vectors. We can also define this operation in the geometrical way, and we have two ways to define this operation. First of all is Parallelogram Rule. For the operation sum or addition. We have two vectors V and U with coincide initial points, and we can construct other two vectors and to construct the parallelogram, and diagonal of this parallelogram is vectors which defined as the sum of the vector U and V. And we denote this vector by as U plus V. That this diagonal is vector A, and by definition A is the sum U and V. And we have also other way to define the addition, operation addition on the vectors. so-called triangle rule. Triangle rule. We have some vector A, B, and maybe other vector C, D. And let's consider vector B, E, which equivalent vector CD. B, E, such vector with initial point which coincide for with endpoint of vector A, B, and vector with initial point A and endpoint E, vector E, AE, is the sum of vectors AB and CD by definition. AE is the sum AB and BE. We can see that the definition of the sum in the second way, we define this operation on the class of equivalency, of equivalence classes of vectors. But we will identify equivalent classes with vectors. And we consider vector as a class of equivalent segments with direction. Let's formulate some basic properties of the operation of addition on vectors. Easy to see that from definition follows the commutativity of this operation. And let's formulate properties. Follow the tradition, first properties is associativity of this operation. If we have three vectors A, B, and C, and we have the following equality. The sum of A, B, and C is equal to the sum A and the sum of B and C for arbitrary A, B, C. From the space phi up 3. The second property is commutativity. For arbitrary easy to prove this property by geometrical way using these geometrical definitions. Commutativity easy to follow from Parallelogram Rule. We can see that we construct parallelogram using vector u and v, and the same result gives the using vector u as the first summand, v and second, and v as the first and u and second summand. And using the second definition, we also construct some parallelogram, and if AB is AV and BE is B, and the same, let AK the vector B, AK is equivalent BE, and KE is equivalent A, and we have A plus B is equal B plus A, or equivalent. The first property can be proved the same way. Let's consider A, B, and C, and this vector is the sum A of B. Oh, I'm sorry. And this vector is the sum A plus B and C. And this vector is the sum B plus C. And A plus this sum B plus C is equal also A sum plus sum B plus C. Sum B and C. And we have this equality. Third property, for any vector A, we have the sum A plus 0 is equal A, is equal 0 plus A. And fourth property, for any vector A exists and unique vector B such that A plus B is equal 0. This vector B is called opposite vector. The B has the same length as the A, but opposite direction. And we also denotes vector B as minus A as a definition of opposite vector. Let's note that this property denotes that the vector are so-called abelian group is a definition of algebraic structure which called abelian group. More precisely, abelian group is a set with some operation which is called by sign plus, and this operation satisfies the following conditional properties. Is an ordinary axiomatic way for definition for some algebraic objects, and some algebraic objects are called abelian groups. So the vectors with some operation is abelian group. Corollary. Is abelian group. But we need in the other operation on the vector. This other operation is called scalar multiplication. We'll consider the real numbers, and these numbers will denote by Greek letters lambda, mu, and we'll call the real numbers by scalar. We introduce the other operation, multiplication by scalar, which operation corresponds to pair real number lambda and vector A, the vector which called lambda multiply A. For example, if we have some vector A and lambda to product 2 and A is a vector which parallel to vector A, has the same direction and the twice length in compare with length of A. Definition 2. Definition of scalar product. Given scalar lambda r and and vector OA the product by a scalar is the such is a vector such that the such vector OB such that the length of vector OB is equal model lambda and length of vector OA. Vector OB is parallel OA, and so property OA and OB have a same orientation if lambda is greater than 0 and the opposite orientation if lambda is smaller 0. If lambda is equal 0, then lambda OA is equal 0 vector. For example, if lambda is equal minus 1 multiply vector A is such vector OB which has the same as vector OA length and opposite direction, and we have the following corollary. If we multiply minus 1 on vector A, we obtain the opposite vector minus A. Minus 1 multiply to vector A is equal opposite vector. As example, if we have vector A and lambda is equal to have such vector OAB to OA and is equal OA plus OA. And if lambda is integer, the product of such lambda and vector I, vector A and A is equal to the sum of the n vector A. If n natural number greater than 0, if n less than 0, and A is equal minus n summand, which of them is equal minus A. We can also formulate some property of this operation, namely property of scalar product. Properties of scalar product. First property. By definition, if we multiply 1 on vector A, we obtain vector A. Second property, if we have two numbers lambda and mu, and if we multiply the sum of these numbers on vector A, we obtain the sum of following two scalar product, lambda A plus mu A for all vector A and all real number lambda mu. Oh, I'm sorry. I'm sorry. This property of two operations, sum and scalar product. For scalar product, we have the following property. If multiply one number lambda on two lambda mu and multiply this product on the vector A, we obtain the product, scalar product number lambda and vector which is a scalar product mu and A. For arbitrary real numbers lambda mu and any vector A. We have the following true property. If this property is very simple, the first property is evident. By definition, we have vector A and product number on this vector is the vector parallel to vector A, this length is the same as the vector A, and direction is the same, and this vector equivalent to A, or equal. The second property also simple, but this property has a long proof. We must consider all cases of signs, numbers lambda and mu, and we must compare left side and right side. First case, when the sign of lambda and mu is the same. For example, let lambda and mu be positive numbers. In this case, the left side, this vector, is equal to such vector which parallel to R, and this length, and its length is equal product lambda mu on length A and lambda mu and A. The right side is a vector with which parallel to the vector A, and this vector has the length which is product lambda length mu A, and is equal model lambda model m model mu and length of A, and is equal lambda mu and length of A. And we can see that this vector left side and right side has the same length and same direction. Then these vectors are equivalent or equal. If both lambda are negative, in this case we change the sign, and in the left side we obtain product this numbers lambda mu, and in this case we also change signs and obtain the same result. And in this case we obtain that this vectors are equivalent. The case when the signs of these numbers are opposite has the same proof. We must to change sign in both and left sides. I suggest consider this case as exercise. The case when the product lambda and mu is negative. The case when one of these numbers is equal 0 is simple. In the left and right side we obtain the 0 vectors in the simple case. Okay, and we have the following property for scalar product, and the two property of scalar product, and four properties for addition operation. And we also have two property which connects these two operations, addition and scalar product, so-called distributivity properties. The following two properties. Namely, for any real numbers lambda mu and any vector A, we have lambda plus mu multiply A is equal lambda A plus mu A. And second property, for any real number lambda and any vectors A, B, we have lambda, scalar product lambda and sum A and B is equal sum following vectors lambda A and lambda B. Summarize these properties, we obtain the following 8 properties. Let's write these properties and we obtain the following collection of the properties of element of V of 3. Eight properties. Associativity property, commutativity property of addition. The first four properties, the properties of addition operation. For any A, any vector A exists such vector minus A that A plus minus A is equal 0. 5 property is the first property of scalar product. 1 multiply A is equal A for arbitrary A from space, vector space. 6 for all real number lambda mu and any vector A. And last two property, distributivity property. And last property, and this property is the first step on the axiomatic way to construct the solid geometry. This property we can consider as the axiom of this vector space. And this axiom is the initial point for this axiomatic way. Easy to see that if we restrict yourself and consider some plane in the space and restrict, and we will consider only vectors which are parallel to this plane. This operation, addition and scalar product, which apply to such vector, in this way we can obtain also the vectors which are parallel to this plane. And in this way we obtain the plane vector geometry. And in this definition we can change number 3 on number 2 in such way we can obtain the plane geometry. Plane geometry V2. We can continue our way and change 2 on 1. We can consider some straight line in the space and consider only the vectors which parallel to this plane. And the sum of such vector is also vector is which parallel to this straight line, and if such vector we multiply on the scalar, we also obtain the vector which parallel to this straight line. And this set is closed under this operation, and we obtain the vector space V up 1. And this vector space is exactly the number of the set of real numbers. We can correspond to any vector unique defined real number lambda, and we can identify V1 with the set of real number R. And this remark is initial point for corresponding for following reasons. For vectors in coordinate systems. In the case of the vectors in the space V1, we fixed some points O and some vectors of unit length, vector E. The length of this vector can be arbitrary, but for simplicity of further reasoning, we can suggest that the length is equal 1. And any vector of the which parallel to this straight line can be obtained as the scalar product of some real number lambda and E. The length of this vector is equal module lambda, and if lambda greater than 0, we have vector which has the same orientation as E and opposite orientation if lambda less than 0. And we obtain one-to-one correspondence between real numbers lambda and vectors and if we have arbitrary vectors which parallel to this straight line, to these vectors, we can present as scalar product some number lambda and vector E. And opposite inverse map is map which mappings A to the lambda, and we have one-to-one correspondence. Let's note that length of this vector can be arbitrary, and if its length is lambda null, the correspondence the number lambda corresponds the ratio of lambda and lambda 0, and inverse mapping corresponds arbitrary vector A, this ratio lambda 0. But this correspondence also bijective, and we in this we also obtain the equivalence of between this vector space V1 and sets of real numbers. In the case V2, we have the same correspondence, and in this case we also can consider two perpendicular vector of unit lengths. Let one of them I will denote by I and other by J. And if we have some vector A, we can present this vector as a sum of two projections, A on the straight line which parallel vector I, and projection of second line which parallel to vector J. And we have two projections, A1 and A2, and two vectors. And after we can use the previous correspondence and corresponds to vector A1 the number, some number which is equal length of this vector, and to vector A2 it also corresponds the number which is length of this vector if A1 has the same orientation as J and length is opposite sign if the orientation of J and A2 are opposite. And we have the following correspondence. We can represent A as a sum A1 and A2, and A1 we can represent a lambda 1 multiply I, and A2 represent as lambda 2 multiply J, using previous correspondence, and corresponds to this vector the pair of real number lambda 1, lambda 2. Easy to see that inverse mapping is defined by this formula lambda 1, lambda 2, it corresponds this sum lambda 1 multiply I plus lambda 2 multiply J, and this vector which V2, and this pair belongs to R2. R2 is direct product R and R. And we obtain one-to-one correspondence between element of V up to and R up to. So, arbitrary vector can be present as a pair of real numbers. And we have one-to-one correspondence. We can continue this reasoning and consider the case of the space. In this case, the reasoning is the same. We must consider triple of the vectors triple of the vectors I, j, and k. And you can consider three straight lines x, y, and z, and if you consider the arbitrary vector A, we can correspond to this vector projection on this straight line. First of all, projection on the plane and onto one of this straight line, and after projection on all this straight line. And on this way we obtain three vectors A1, A2, and A3, sub 3, and we can present vector A as a sum of these three vectors. And each of these vectors we can present as scalar product of some real numbers lambda 1 on I lambda 2 multiply to j and lambda 3 multiply to k, and corresponds this vector the triple lambda 1, lambda sub 1, lambda sub 2, lambda sub 3, and this triple is the element of R3. And this one-to-one correspondence we have inverse mapping, which defined the same way. And after them we would like to continue this way and consider the case when n is equal 4. For example, in this way we can try to describe the physical space to add to the space coordinates, the force coordinate, the time, and consider the point as the element of such space-time big space, which is space-time. And we can use the abstract point of view and consider the arbitrary n, and such imagined vector space, the element of this space we one-to-one correspond to the n tuple lambda 1, lambda 2, lambda n. I'm sorry, the element of this space one-to-one corresponds the n tuple, the element of R up n, the direct product of n copies of real numbers R. And in such way we obtain the abstract vector space. easy to see that for element of this space fulfilled all axioms, but also easy to see that operation on this space can be defined by the following formulas. If we have, first of all, consider the case of the plane. And we have two vectors, vector A, vector B, and let B1, B2 be the coordinates. Oh, I'm sorry, maybe lambda 1, lambda 2, the coordinates of vector B. And mu1, mu2, the coordinates of vector A. And easy to see, the coordinates of vector AB is lambda 1 plus mu1, lambda 2 plus mu2. We can also obtain this equality as a corollary from this axiom and operation addition and scalar product. Exactly, we have A is equal lambda 1 I, lambda 2, B is equal lambda 1 I, lambda 2 G. A is equal mu 1 I plus mu 2 G, and this sum is equal A plus 1 lambda 1 I lambda 2 G plus and using this axiom we can obtain the following formula: lambda 1 I plus mu 1 I plus lambda 2 G plus mu 2 G, and using distributivity axiom we obtain lambda 1 plus and we obtain that coordinates of this vector is the following sums. And also we can obtain that if we multiply vector A on some number mu, the coordinates of this vector is equal mu 1, mu 2. So this reasoning can be applied to the general case when we work to n-dimensional space, and we can define on this space the algebraic operation of addition and scalar product by the same formulas. Namely, we can define abstract arithmetic vector space Rn as the set of such n tuples with the following two algebraic operation. One of them, the operation addition, is equal by definition and the second operation scalar product, is defined by the following formulas. Easy exercise. This operation, these operations are satisfied to the following 8 axioms. To prove that above defined operation of addition and scalar product operations are satisfied the above mentioned 8 axioms. On vector space. So we obtain some examples of vector space. See geometrical example, line geometry, plane geometry, and solid space geometry, and example of multidimensional geometry or geometry in n space. Last example is rather arithmetical or algebraic, but in this case we also can use our geometrical intuition to formulate some assertion about the geometrical locus in this abstract n-dimensional space. These locuses can be described only by algebraic or arithmetical methods using equation or some inequalities, and we will move on this way, and we need some definition. Сколько мне еще времени? 5 минут. I haven't enough time, but I try some important definition, and I continue on the following lecture this way. I need in the following important notion of linear independent vectors, and main notion of the basis in the vector space. This central notion of our further consideration. Let's formulate first of these notions. Let W is a vector in the some vector space V. We said that V is linear combination of the vector V1, V2, Vr, if the vector W can be expressed in the following form as lambda V1, lambda 2, or lambda n Vn. Such expression is called as linear combination. In this notation, lambda 1, lambda n is a number, and V1, Vn be the vectors. Linear combination. I have time for continue this line, and we finished in this place, but then on the next section I continue our reasoning. Thank you for your attention. Bye bye.